Finished my general announcements. The work for 9.1 is due today. We're going to continue our discussion of 9.2 today. I project to finish 9.2 Tuesday next week, which is why the 9.2 work is due on Wednesday next week. Keep in mind, we're still slated for the Chapter 9 test to be on Monday, March 17th. Yes, 17th. All right. So this formula is actually something that was presented all the way back in Chapter 2. And that was if you want to calculate a standardized test statistic. So if you want to calculate how unusual is a thing relative to the population it came from, this is the formula you use. And it doesn't matter if you're talking about individuals that are part of a population, or if you're talking about a sample result that is, in theory, part of a population of potential sample results, what we call a sampling distribution. Okay, let's make sure we have those earbuds and phones put away, folks. I appreciate it. All right, so with 9.22, it says you plan to perform a test using the null assumption that the proportion is 30%. You're looking for evidence that it's actually less than 30%. A simple random sample size 50 from the population yields 11 successes. So you observed 22%. The question is, how unusual is that? That's what a standardized test statistic is used for. And you are following this structure. You are simply entering, what was my statistic? What was the parameter that I assumed was true? And then we have to do a little bit of work for the denominator. That's going to be the square root of p times 1 minus p over the square root of the sample, over the sample size, excuse me. So this formula is literally saying, how unusual is 22% when I expected 30% to actually be what should happen? And the denominator describes typical variation from 30% in samples of 50. I would argue that that number is probably fairly large, meaning the standard deviation, because the sample size of 50 really isn't all that big. So I wouldn't be surprised if that's a standard deviation of 4, 5, 6, 7%. Okay, so this difference of 8% is apparently a little over 1 standard deviation. So that kind of aligns with what I was just saying. I suspect the standard deviation is fairly large. So being 8% apart is only 1.2 standard deviations apart. Okay. So assume the conditions for carrying out the test are met, find the p-value. This is nothing more than, if you imagine the image, we assumed 30%. We actually observed 22%. This is the difference between p and p hat, by the way. So pay attention to notation. And it turns out if 30% really is accurate, well, then the probability of observing 22% or lower is what we consider a p-value. And that's what we use the normal CDF command for. So apparently there's a 10% chance of getting a result like that in samples of 50 if the true proportion really is 30%. I went through that really fast, so don't be shy about asking questions. So in this particular case, you observed 18%. I don't know exactly where that would be on the normal curve, but it is clearly lower than 22%. So you should already anticipate you're going to get a smaller p-value. If you didn't get a smaller p-value, you did something off. If you didn't get a larger negative z-score, something you did was off. Okay, so you should have gotten a z-score of negative 1.8, which resulted in a p-value of about 3%. Now the question says, what if you're working at a 5% significance level? Would you come to the same conclusion? In a word, the answer is no. Okay, because they're basically saying we need to observe something that is 5% rare. Well, the first thing is going to happen 10% of the time. The second thing is going to happen 3% of the time. So they are on different sides of that fence. For that reason, if you're working at a 5% significance level, if you observed 22%, that is not low enough under 30% to convince you. So again, you have some evidence. The true proportion is lower than 30, but it wasn't convincing. So if you build an interval centered on 22%, that interval is going to contain 30 because 30 is one of the plausible values. But if you are in the second scenario where you observed 18%, that is far enough below that if you built an interval around that 18%, it's not going to reach back up to 30. It's going to create an interval entirely under 30, which aligns with the idea that you'd be rejecting. That's essentially what I said here. I said, well, if you're going to use 10.8%, it's going to be greater than 5%. You'd fail to reject. Okay, there's not enough evidence showing that p is lower than 30. Okay, however, with 0.032, it's less than 5%, so you would reject. Now, obviously, your style of writing is going to be different, but what I would say the key features that should definitely be part is you have got to communicate that you recognize the two p-values are on opposing sides of 5%. One is greater, one is less than. And you have to connect that that thing that you notice to, well, one decision would be reject and one decision would be fail to reject. As long as you have those elements and you have some form of context, I mean, here we don't really have context. That's why I use proportion is less than 30. I'm fine. Okay. So this is no, this p-value is greater, this p-value is less than. So here I'd fail to reject, there I would reject. That's basically what a complete answer, those are the components of a complete answer. Questions? All right, on TV shows that feature single singing competitions, contestants often wonder if there's an advantage in performing last. To investigate, researchers selected a random sample of 600 college students and showed each student the audition video of 12 different singers. Each student viewed the videos in random order. We would expect approximately 1 out of 12 of the students to prefer the last singer seen, assuming order doesn't matter. In this study, 59 of the 600 students prefer the last singer they viewed. We want to perform a test at a 5% significance level using the null is 1/12, and then we're looking to see, well, is there evidence that more than 1/12 of the time the last person wins, where P is the true proportion of college students who prefer the last singer they see. So the picture here, in case we're not clear on this, is I show each of you the same 12 people, but in a completely random order. Now, if you all are unbiased, if it doesn't matter the order and whoever you view last doesn't have an advantage, well, then really what we should see is whoever the better singer is, they're getting picked. It might be the third person for him. It might be the fifth person for her. It might be the seventh person for him. Whoever's the best singer, they should be winning. Okay. But if there really is no relationship and all the singers the same skill level, well, then they should each win 1/12 of the votes, unless just being watched last is an advantage. Okay. Now, we're about to predict what should happen in situations like this. We're about to predict that if you go out and do this with 600 people, I'll tell you what kind of results you should get. Okay. Again, that's like mathematicians claiming to have a magic 8-ball. What justifies that is, do you have certain conditions satisfied? Okay. So they took a random sample. Okay. They randomize the order. This is almost like an experiment. They're randomizing the treatments. Okay. They have a random order, random sample of singers. 600 college students, definitely less than 10% of all potential college students. So I'm not worried about the probability of success being altered just because I pick one student after another. And then finally, would the shape of the distribution of potential results actually be centered unimodal around 1/12? So in other words, do you have enough data to justify the shape of the sampling distribution should be normal? Now, this is the only part of this page I was planning to do for you. The rest is going to be on you all. It's calculate the standardized test statistics. So figure out the z-score, find the p-value, and then write a conclusion. Okay, go. All right, so I gave students time to work ahead of me on this problem after we did part A together. Okay, here is the work for the z-score in B, the p-value in C, and then the conclusion in D. Okay, and again, the image of what's going on here is we assumed 1/12, which is about 8%. And what we actually observed was 9.83%. So this is p hat when we assume the proportion was p. And what we found was, if it truly is 1 out of 12, when the probability you're going to see that much of a proportion or higher just by chance is 9.22%. So in other words, we don't really have convincing evidence, at least from this data, that going last is in fact an advantage. Because while the person who went last did win more than we would have expected them to, it wasn't significantly more. Okay, it's an amount that could have happened by chance. Questions? All right, turn the page. So this box up top, it basically has a strategy for how to map out a hypothesis test. Okay, and I want to be clear that in the future and on the AP exam, you're not going to have this box structure in front of you. They're not going to walk you through the process. It's literally just going to say, here's the problem, run a significance test, and it's going to be a big blank slate. So I think having this mindset of, I need to state what I'm actually going to do. So set up your hypotheses and your parameter. That's what the first thing is. I will admit I don't do this part. What I highlighted in orange, I kind of leave that for my conclusion. I always state my significance level as part of my conclusion. So that'll be the only part of this box I don't totally align with. Okay, my first box is I set up my hypotheses, I define my parameter. My second box, the plan. Why are you allowed to do? What is it that you want to do, and why are you allowed to do it? So I state the type of test that I'm going to actually run, and I list out the necessary conditions. So that's me just setting the stage of what I want to do. Then we move to the do phase, what I like to refer to as the mechanics. That's the calculation. So in this case, you want to give what was the thing that you actually observed? What was the statistic you actually got? How does that compare to what you thought you were going to get? So find how weird it is, meaning a standardized test statistic, and then find the probability that you would see that just by chance. That's a p-value. And then the last part is your conclusion, which is basically just deciding, should you be rejecting or failing to reject, and make sure your conclusion is always in context. Okay, so that's sort of a four-pronged structure that you can follow to help you map out a complete answer to a hypothesis test. Questions on that? All right, then you've got 8 minutes. I don't think that's enough time to finish. Some of you that might be fast enough, but I want to save some time for the last thing I wanted to get to today. So 8 minutes, get as much as you can done. And again, I will be calling on people at random for parts, and I'll go in order. I'll go state, plan, do, conclude when I call on people. Go. All right, I gave students 8 minutes to work ahead of me on 9.24. Here is the completed work. I want to address a question that came up, which was, do I have to do this? In truth, the way the grading rubric reads on the AP exam is, was the test identified by name or formula? So if you show this work, you are making it clear that you're running a 1 proportion Z test. So if you have one, you don't need the other. Okay, but I think knowing this, while right now we might not totally appreciate it, when we're totally done with all the different hypothesis tests, you all will have 9 options to choose from. That sounds scary, but there's a family of 3 that are basically the same test. There's another family of 3 that are basically the same test. And then there's proportions, means, and categorical data. So it sounds scary when I say there are 9 different tests. It's not that bad. Okay. Questions? All right, last thing I want to get to today, and we're not going to see full hypothesis tests of this today. We'll get into it on Monday, but I just wanted to address a really common mistake. We already should hopefully know that if you're looking for evidence that the true proportion is less than some claim value, or if you're looking for evidence the true proportion is greater than some claim value, that makes it a one-sided test. If you're looking for evidence that it's just not whatever the claim value is, like I think it's something else, and you didn't really specify greater than or less than, that's a two-sided test. Now, the common mistake that comes up specifically with two-sided tests is that if you are interested in, okay, I think it's this value, I wonder if it's not, well, when you collect data, you can't land on both the high and low end at the same time. Okay, you can only land on one side or the other. So what ends up happening is people find, okay, this was the result I got, so this is my p-value. Wrong. If it's a one-sided test and you observe this, then this is your p-value. And the way you put it in context is you say, all right, if this center value really is true, the probability of landing this low or lower is blah, blah, blah. However, if it's a two-sided test, and so you're interested in collecting data that it's just not this thing, it doesn't matter to us if it's on the low end or the high end. What we want to do is we want to find the area under the tail on the side that we observed and double it. So if this is 3%, your p-value is actually 6%. And instead of saying, well, there's a 3% chance I land this low or lower, we say there's a 6% chance you would land this far away or further. Does that make sense? And the common mistake that people mess up in a two-sided test with their mechanics is they get the area in one tail and they forget to double it. They forget that they're not just fixated on the low end, or they're not just fixated on the high end. You shouldn't be fixated on the side you happen to land on. Okay, you should be thinking about both sides simultaneously in a two-sided test. Okay, so here's two examples of this, and then we'll call it a day. Suppose that you want to perform a test using the assumption of 30%. You're looking for evidence it's not 30%. A simple random sample from the population yields 19 successes, which is far beyond 30%. Okay, it's at 38%. If you're going to calculate the standardized test statistic, nothing is going to change. You are still doing the exact same thing you would do, regardless of whether it's one or two-sided. How weird is 38% when I assumed it was 30%, and that denominator is typical variation from 30% in samples of 50. Turns out that it's about 1.234 standard deviations above expected. However, this is not your p-value. Okay, that's only one side. If you're going to stop there, you're treating it as though this, was greater than 30. If you stop there, that's what you're doing. And so if I was going to put that red wrong number into context, I would say, all right, if the true proportion really is 30%, then the probability of observing 38% or more is 10.9%. But that's not what I'm interested in. I'm interested in what is the probability of landing that far away or further. So we may have landed 8% too high, but we have to admit, if the true answer really is 30, you are equally likely to land 8% or lower. Okay, so if that's the probability of landing at 38 and above, that's also the probability of landing 22 and below. So what you have to do is double it. Take your p-value that's on one side and double it. And now that's the correct p-value. And that p-value in context says, okay, if the true proportion is really 30%, then the probability of landing 8% away or further is 21.8%, which, by the way, in most cases, that's going to fail to reject. That's a very large p-value. So we would say, all right, well, that 21% is greater than 5%, so we fail to reject. We didn't find evidence that it's not 30. Like, yeah, we landed far away, but it wasn't far enough away to convince us it's not 30. Questions? All right. This is your time to try the last problem of the day yourselves. If you want hints, look at the board. If you don't want hints, don't look at the board. Go. All right, so hopefully you got a one-sided p-value of 1.25%, which is a two-sided p-value of 2.5%. All right, and we'll see two-sided tests on Monday. Thanks for watching. Have a good one.